You can erase the chip first and then read it, because the chip erase command only erases flash memory. And this is very common. Erasing flash memory and erasing RAM are very different operations. To erase flash memory, you have to build up a charge pump, you have to start a clock, the clock has to hit the flash in proper sequence. And instead of doing that, it's a lot easier to just erase flash memory, because that's where the secrets that the vendor is concerned about reside in. If I get flash memory, I can plagiarize a design. And that's what they're worried about. That's what they're defending against. In the same way that on your PC you might defend against malware. The problem is that these devices are now being networked. So when you throw one of these on an IPv6 network, and it has keys, and those keys are stored in RAM, they can be extracted from the device by erasing its flash and reading out its RAM. You have one dud device that costs $10 that's meant to be disposable. The attacker has your keys. And there's no way to patch this. There's no way to keep RAM from being exposed. You can replace the firmware to not store the keys in RAM, but that becomes very difficult with things like session keys. And reflashing the chip for every session key is not manageable. So to erase and then dump, all you do is erase the chip, copy out its RAM, and then search that block of RAM for the keys. To glitch it until it's unlocked, all you do is keep re-entering the chip and hit the voltage rail with spikes downward. Keep dropping its voltage low, and I'll show you later how to figure out exactly how low. But the thing that I kept getting in reply to this, to that old stuff, was this Florida regulation and similar laws that you're not allowed to tamper with the device. That there's some holy grail about physical interaction with the target. An attacker can never set foot on your property. He can never open up the box. He can never get a screwdriver or a logic probe or anything like that. So I said, okay. And I started playing with the ZStack software using the debugger. The ZStack uses, the ZStack from Chipcon uses a hardware pseudo-random number generator, which is seeded by a true random number generator in the radio. The seed state, I think, is sufficiently random. I don't know that it's perfect, but it's pretty damn close. The pseudo-random number generator, though, has a really small seed. Its entire state is 16 bits, and half of the bits are being skipped. And when you try to test this, you can't just recompile the code, because it uses a chip-specific hardware device. It's not calling this LFSR function. It's writing a value into one register and reading a value out of another, like a magic address in RAM that just happens to have a function attached to it. And you can't simulate it unless someone has added this feature to a simulator. What you can do is debug it and trace it and copy it out that way. So I used Wine to install the publicly available demo of this software. Once I had it, I wrote this dandy little code in Python. All it does is run through RAM and copy bytes out to a file based upon tags that are placed in RAM. So I've got dead or beef in an address. Dead means it's ready, beef means it's not, or vice versa. And I just keep freezing it and releasing it until I get my values out. On the C side, this is on the target, this is not on the debugger. I run a C program on the chip that calls the library that I'm interested in auditing. This C application runs on the target itself, and it's running the actual demo code that's shipped with the chip. I'm using a different compiler, but aside from that, it's the same thing. And I put this little fragment of machine language in. A5 is not a valid 8051 instruction. It's the only opcode that is not defined for the 8051. Everything else means something. A5 was left to be chip-specific by the instruction set designer. And for good reason. He thought if they had 10 extra instructions available, people would use all of them. But if he left just one, and he left instructions that it never be changed or defined to be anything, then that might survive. So A5 is a software breakpoint. You call that at the end of the loop, and it will wait for the debugger to restart the application from exactly where it left off. So in each iteration of the loop, you just wait for a while as the debugger copies all of the values out, dumps them into a file, and then you can continue on. This is a histogram that I generated of the hardware random number generator. You'll see that the byte as a whole is not the least bit random, but if you look only at the least significant bit, it actually does appear to be rather random. I won't say perfect because there's a much bigger issue. The pseudo-random number generator has 1 byte per tick, so it's actually going through 15 bits of its address space. And these are the bytes that I dumped by the debugger. This is from hex dump to head. So all of the bytes that you see here are the very beginning of the dump. And I took that beginning and I just grabbed a couple of bytes at random and I grepped for them with color. I love this switch. So you see, there are the bytes, and there they are again, and there they are again, and there they are again. And the difference between them is 2 to the 15th power bytes minus 1. That's just a little bit more than 32,000. And you can try every AES key in this range in very short time on your PC. There's also a dandy AES accelerator in every one of these chips. So if you had like a worm that was trying to spread through them, any chip that had been infected could be used as a computational node with hardware acceleration to try and break the rest. And it also has the random number generator installed, so it doesn't need this list. It can generate it itself as it's needed. Just feeding them into the AES register until things make sense. The usage in the Zigbee stack is that they've got this function keygen, or it has a longer name. It just takes a pointer and a length, and it populates at that pointer with length number of random bytes from the getRandByte function. And all this does is call the low or high word of the PRNG, and then clock it once more. Now, which word you get is determined by the starting state. And the starting state is random. So it will actually choose one of 2 32 kilobyte cycles, and it never jumps between them. So you've got 64 kilobytes to look through the first time. For any guess after that, you've only got 32 kilobytes to look through. Or, if they're generated in a row, one will be right after the other. It's quite convenient. So the idea is that you've got all of this stuff that doesn't seem to have that much to do with security. All of this general development stuff for legitimate engineering value, in the same way that in order to do computer security work, you have to have a good compiler, you have to have a good command line, a good text editor, when a text editor itself has very little to do with security. Here, the tools are often unavailable until you bother to make them. This platform that I'm making, though, is open under the BSD license and beerware. And if you want to rip me off and put anything else on it, we have the fuck you neighbor protocol. So if you steal it and you put it in a commercial product and you pretend that I had nothing to do with it, and then later on you get sued and you point them back at me, you can say, fuck you, neighbor, and I can say, fuck you too, neighbor, and we can high five. This is the next chip that I want to talk about. And I've got to speed up. I have too many slides. This is the MSP430. This is an early prototype that I got. And I like this chip because it's windowed. You can actually see that there's a chip inside. They didn't do this because they wanted to. They did this because it helps by UV erasure. So you have to stick this thing in a UV oven for half an hour, and when you take it out, all of the bits have become ones. You can move them back to 0, but not up to 1. This is a more modern board. And they have a really cool one that just came out as a Zigbee wristwatch using a descendant of this chip. So for $50, you can get a chip that will run as long, or a watch that will run for as long as any other wristwatch. But it also speaks to computers around you, so you can have it announced to your workstation that you walked into the room. And unlike the Zigbee watches, you don't have to recharge it every day or lug around a heavy battery. So back to JTAG. Even within a family, like the MSP430, you have variants between protocols. The MSP430 classic protocol is actually from the first flash generation of their chip, which was the first that could be programmed by JTAG. It was a 16-bit chip, by which I mean instructions are 16 bits wide, and so are pointers.